It's really good to be there after all these years. Well, so, yeah, as you said, the title is inspired from Pretty Little Liars, and actually the title is a lie. I won't be talking about compilers design, and a better title would have been, oh, does it work? Oh, write schemas and generate everything else. But now that we've seen the excellent talk from Jakubs yesterday, maybe a better title would be Smithy for Us ruined my talk. Because what I want to talk about is very similar to what is done in Smithy for Us. But without further ado, let's dive into it. So we've probably noticed that our code bases are getting more and more complex, and that we are mixing more and more technologies and languages into them. Of course, at the very center, there is our beloved production code. But around it, we have many other actors. We have our tests, unit tests, integration tests. We may also have YAML definitions of our CI pipelines, or scripts for running all the things in production. And lately, I've also seen an increasing number of teams using some sort of specification or documentation or schemas, be it OpenAPI, protocol buffers, async API, Smithy, you name it. And that's good. But the thing is, these documentations and specification and schemas, they are not invited to the CI party. And so they remain there, half forgotten, and they get rusty. And as Jakub said yesterday, there is nothing more sad than documentation that lies, because it became out of date. So how could we solve this problem? Well, you could say, that's easy. With Swagger or with Tapir, I can generate my documentation from my code. And that would be a perfectly fine solution if you are only building a public-facing API, because you don't need to negotiate with your users. But everything that is internal, you need to do some sort of negotiation between teams or business units. And if the documentation or the contract is extracted from the code, it means that you get it at a time where negotiation is not an option anymore, because you've written the code and you made pull requests, review them, and so on. So instead of that, when you have internal APIs, I think, and I want to convince you, that you could and you should build your own solution to this problem. And that's what I want to show you today, that we can quite easily and quite cheaply build things that will put the documentation or the schemas inside the CI loop, making us able to have them already always up to date and accurate. There are many things we can do. For example, you could take your schema or your OpenAPI spec, for example, and use the examples and the schemas inside the OpenAPI spec to generate integration tests that will verify that for this given example of a request, the actual server actually answers the response that you have in your OpenAPI file. That's doable. I have no time for this kind of idea today, so I will just focus on one thing, that is writing a compiler for it. Hopefully, Martin is not in the room anymore, so he won't be throwing rocks at me, because I have a very liberal definition of a compiler. A compiler, for me, is something that takes some data that is in sequential format, be it a text file, for example. It then builds a tree out of this linear shaped thing. It does some transformation and verification on the tree, like type inference and so on. And finally, it use that tree to spit out another thing that is linear in structure. For example, the Scalar compiler, it takes your Scala code, which are just a sequence of characters in a file. It builds an AST, it does a lot of things, optimization, type verification, and so on and so forth. And at the end, it spits out bytecode, which is also a sequence of bytes. Or we could say, that's where Martin would probably throw rocks at me, if we take a schema, which is a text file, build a tree, and then, for example, generate Scala source code out of this schema, that's the same ID. So that's why I call that a compiler. And I argue that for doing that, you only really need what's on that slide. Nothing more. I've done it, so I know that I'm right. So at the top, you have the definition of hydromorphism that you can find in the Drosty library. Drosty is a library for recursion schemes. I don't have time today for talking more about recursion schemes. Me and others have done it many times before. But let's assume that everybody knows about it. Recursion schemes is a set of mathematically inspired techniques for dealing with recursion and recursive data structures. So everything we need to do with our tree, we will do with recursion schemes. Over. Then, something that probably you've not been familiar with is what's called the contravariant monoidal syntax. It's fairly simple. It should be similar to something you're more familiar with, which is the applicative syntax. And I will go quickly over it. So the first thing here is what we call forget left. Given an f of unit on the left and an f of a, we can combine those together and get another f of a. We just forget what the f of unit does. We have similarly forget right, that does the same thing but the other way around. I have an f of a, I can combine it with an f of unit, and it gives me back an f of a, forgetting what the f of unit does. Then we have this operator I call whiskers that just combines an f of a and an f of b and gives you back an f of a pair ab. And finally, we have this choose operator that also combines an f of a and an f of b, but gives you back an f of either ab. And that will allow you to choose which path you want to take. So let's see a few examples. So let's see a very, very simple contravariant functor. Don't be scared by the name. A contravariant functor is a functor, but with every arrows reversed. So let's say I call printer the polymorphic function that takes an a and returns a string. That's, by definition, a contravariant functor, and a contravariant functor is, as opposed to covariant functor, on which you can modify the results using map. A contravariant functor, you will pre-process the arguments using contramap. So if I have an f of a that is contravariant, and I want an f of b, I need to contramap a function from b to a. So with that printer, we can define a few useful small printers. For example, the string printer is just the identity function. It takes a string, returns a string. That's it. Or I can have the constant printer. I initialize it with a constant, and it will give me back a printer of unit that, regardless of the input, will return my constant. And now with my combinators, I can combine both printers to make a greeting printer that will be a function that takes a string, which is the name of someone, and prints hello, the name. That's using forget left and forget right. I just don't care about the unit printers, the constant ones, and I just care about the string one. So far, so good? Cool. Oops, sorry. Then I can combine two printers of things that are useful into a printer of pair of things. So for example, if I have the int printer that takes an int and returns a string by calling toString on it, I can build a weather printer that will take the name of a location, a forecasted temperature, and print today in the location, the temperature will be that number. So in the world of, oh, come on. Well, too bad. So in the world of contravariant, yeah, that's it. In the world of contravariant functors, I have the same idea as applicative functors in the world of covariant functors. So the same way we have map n with regular covariant functor, I can have contramap n that will allow me to bundle a bunch of such f's into a tuple, and then pass a function that will somehow not combine them, but explode them into a new printer. So for example, let's say I have a conference case class that has 3 fields: the name of the conference, the location, and the temperature forecasted for today. I can bundle the 3 printers that I have already defined and massage the inputs. And massage the inputs so that I extract from the case class object the parameters for my different printers. So for the grid printer, I need the conference name. For the new line, which is just printing a new line, I don't need anything, I put unit. And for the weather forecast, I need to have the location and the temperature that I bundle in a tuple. And that way I can greet the conference and say, hello Scalar, today in Warsaw it will be 12 degrees, maybe more. And finally, the choose operator allows me to decide what to do depending on my input. So let's say I am a bartender. When someone orders me a drink, I first need to verify that this person is old enough to drink in this country. So I create the bartender printer by combining the drink that will actually serve the drink and the too young that will say, no, you're too young, using the choose operator. So I have drink on the left, too young on the right. So when someone gives me an order, I first check the age of that person. If they're old enough, I want to serve them the drink, so I return the left. And if they're too young, I don't want to serve them the drink, so I return the right. And that's it for all this syntax. Now, a little bit of story of what I actually did with this syntax. So I worked for a company a few years ago, 1 year ago. They were building and maintaining a pretty large fleet of microservices that were exchanging messages through Kafka topics. And they had this very good idea of maintaining a Git repository with async API specifications of all the channels throughout the whole system. And they also implemented a pretty strict discipline about maintaining this schema repository. Every time you would make a pull request on a service that would touch something around serialization, you had to make a companion pull request on the event, they call that event contract, on the schema repository. And of course, it would be reviewed, and once the pull request on the schemas was accepted, you could merge your pull request on the service. The thing is, despite all this discipline, there were some inaccuracies in the schemas anyway. And that was a bit frustrating, because when you wanted to build a new service that you knew would need these messages from this channel, you read the schema and say, OK, I will create this case class. But then when you integrate, you realize that there was a typo in a field name in the schema. And also, it was frustrating because it was additional work to do. You had to maintain the schemas. So I got frustrated about it, and I asked if I could have some time to do something. They said no, because there was too much work to do. Then they hired a few more engineers to the team, and they also got frustrated about the additive work and the fact that there were typos or inaccuracies in the types and so on. So I repeated, I have a solution for that, an idea of a solution. I would like to try that. And eventually, like 6 months later, the amount of work of the team decreased a little bit. And so they gave me a sprint, so 2 weeks, to build a proof of concept of my ID. And using the syntax that I showed you, I managed to have a proof of concept working in 2 weeks. So what's the idea? So I built a SBT plugin that would take the schemas from the schemas repository and generate Scalar ADTs with JSON codecs and Scalar check generators out of the types described in the schemas. Using that, I then defined unit tests that would verify that the production code, the actual ADTs and codecs, would behave the same in respect with JSON serialization with my codecs and ADTs generated from the schemas. So for the production code, there was already codecs and Scalar check generators. So I could say, generate me an object, a production object, serialize it to JSON, then deserialize it to a schema object, then back through JSON to the production object. And if both were the same, I had half of the test done. I also needed to do the test the other way around, generate me a schema object, serialize it to JSON, deserialize it to production object, then back to JSON to schema object, and verify that at the beginning and the end, I had the same things. So these tests were pretty easy to write. It's just a Scalar check property. And of course, they showed that the schemas were completely wrong. Well, not completely wrong, but there were inaccuracies. So Scalar check could easily find examples where the schema and the actual production code wouldn't behave the same. But the cool thing is that with this test in place, I could now modify the schemas until the test pass, and then make a pull request on the schema repository, a pull request on my service, and from now on, my schema will remain 100% accurate in respect with the production code because there is a test. So if I mess up and don't change the schema with the production code or the other way around, the test will break. So that was cool. The next step was, OK, so this whole process took me a month and a half. But from the proof of concept to the finished product, yeah, it took a few weeks. And after that, we could even go one step further and say, OK, we now have a tool for generating correct code out of schemas. So why would we bother writing the production code? So when I left this client, they had completely changed the way they approached serialization and messages in their applications, because now 2 teams could gather in a meeting, agree on a schema, write the schema during the meeting, and 5 minutes after the meeting ended, both teams had all the code they needed to start working. And they would never have to synchronize again, because they agreed on the schema. And from the schema, they got everything else. So in the 10 last minutes, I want just to show you give you a taste of how you could develop such code generators. So the idea is you start from top to bottom, and you start with the structure you know you want in your file or in your result. You don't know yet what input you will need, but you know the structure you want. So for example, let's say we want to generate a Scala file that defines a case class with a companion object containing codecs. For the sake of time, we won't get into the companion object, but let's keep it on the slide anyway. So what's the structure of such a file? Well, at the top, you have a package statement. Then you have the case class definition. And finally, the companion object. And new lines between each of these things. So you define that. My Scala case class will be a printer of something that will output the file. And it will need a printer for the package statement, a printer for the case class definition, and one for the companion object. So let's dive into it. The package statement one is pretty easy. It's just the constant package with a space and the name of the package. So it's just a printer of string. Easy peasy. The case class definition is a little bit more complicated. What we need is a name, an open parenthesis, a bunch of fields, and a closing parenthesis. So that's what you have on the screen. The sep by operator here, it simply takes a printer of A and a separator string, and it gives you back a printer of list of A. So here, field will be a printer for a singular field, and I will need to define that now. And a field is just a name, followed by a colon, followed by either a type name or an option of something, depending on whether the field is required or not. But that's where things start to be a little bit inconvenient. It's when you start climbing back up to know what would I need as an input to my Scala case class printer. So let's find out. If you are able to parse this, you will realize that my field printer, it needs a string and a list of a pair of string and either string. Let me decompose that. The first string is this str here. And then we have either str, that's the field name, that's the type name, but the type name can be either directly put or wrapped into options. So I need to choose whether I will put it directly or wrapped into option. So that gives me a printer of a pair of string and either string. See where it's going. One step up, my case class definition is now a printer of a pair of string and a list of pair of string, either string. And of course, if I go one step up, and I've completely ignored the companion object definition, my type is this horror there. So what can I do about it? Well, actually, there is not much I can do. See, the problem is with covariant functors, when, for example, we map n over a bunch of f's, like when we build validations, we need to provide a function from a tuple to the type we want. And fortunately, we have syntactic sugar that hides this tuple from us. So we don't see it. It's the same complexity as with contravariant functor, but just we don't see it. The problem with contravariant functors is that you need to create that tuple, not to absorb it. So you cannot hide it. There is no syntactic sugar for that. And of course, here it's a very simple example, but when things get a bit more complex, you tend to have big tuples. So a solution would be to give a name to all these tuples and create a whole lot of case classes but finding names is difficult, so yeah. So we have no choice. We have to somehow create that big tuple that is ugly. If we want to hide it from the type, we need to contramap something to just go from the type we want, here object schema, to that big tuple. So it won't show up in the types, but it will still show up in the code, and you will have to make sure that it has the correct structure. Fortunately, the compiler will tell you if you mess up and flip a bunch of parentheses there, it won't compile. But still, that code is not the most prettiest. That's the price. And it goes even worse when it comes to ithers. Remember, this is meant to be embedded in a SBT project, so Scalar 3 is out the window. So when you want to build complex printers with many choose operators, the types can become a little bit ugly, even uglier than with just the tuples. Can someone figure out what will be the type of this printer? Any idea? Well, of course, it will be a bunch of nested ithers. Actually, we have even less syntactic sugar here, because for tuples, we have this syntactic sugar that we can name a type with parentheses instead of writing tuple2 bracket, blah, blah, blah. With either, we don't have this syntactic sugar, so it's even more ugly. But we can get back our syntactic sugar, at least in Scalar 2. In Scalar 3, there will be no problem, because there is the pipe operator. But we can create sort of a poor man's pipe operator in Scalar 2 by just saying either is pipe. And then we define a bunch of type aliases, and it gets a little bit less uglier. We can also provide a bunch of helper methods to create values of these nested ithers, because we always need to create these values. That's what our contramap, the function we pass to contramap, need to return. So a good trick is to define a companion object to your type alias and put the helper methods in the same order as you defined the alias. So here I have trait name, case class def, object name. So I put my 3 methods in the same order. And I want to go from a trait name to an ADTF. It's just a bunch of as left, as right, as left. The cool thing by doing so is that if I add a new case, because I realize that I need one more branch in my printer, I just had the case at the end, had a method, corresponding method at the end here, and I just plug a bunch of .asWrite to all the previously existing. So it's pretty mechanical. It's a lot of boilerplate, but once you get used to it, it's pretty easy to do. And that's how I managed to build this solution for the client in such a short amount of time. Anyway, you've probably been lost at some point with all this code on the slides. And honestly, that's not the main takeaway I want you to take away from the talk. The main takeaway I'd like to emphasize is that when it comes to schemas and API specifications in general, I really think we should find a way to go contract first. To first build the schemas and have the tooling for ripping off all the ROI we can from the amount of work it takes to write the schemas. Because if we do that after the fact, we do the work twice. And we lose the fact that these schemas and specifications are meant as communication tools. So if you remember only one thing from the talk, remember that, contract first. And of course, if you want to get back to the weird syntax, Everything is inspired from a library called schemas that you can fetch online and start using and modify and extend. That's basically what I did for this project. And that's it for me. I have 30 seconds left. So with my 30 seconds, I want to promote a conference you probably haven't heard of. It will have 2 editions, one in Seattle and one in Madrid. It's called Scalar Days, in case you haven't heard of it. And now I have 10 seconds for questions.
I do have a question. Thank you very much for the talk. It was brilliant, and I loved the art that went with it. The actual question, though, is you had to generate a lot of boilerplate code for the easers in the end, nested easers. Have you thought of going really meta and having a schema for the subset of scalars that you generated for, so that you could generate the types for that, so that you could generate the printers?
Oh, you mean make the code generator generated from a schema?
Yes. I'm not sure it's useful. It just sounds very fun.
Yeah, it will be fun. So that probably the idea struck me at some point. But the printer part is not all there is. There is also a lot of things you have to do with the trees. And actually, that's also something I wanted to emphasize. That's why I didn't make a library out of this project. That's because every organization has their own take on what a schema means. And so I would prefer to empower you to do the tooling yourself, the tool you actually need, rather than that. And everything is actually in the tree manipulation. The scalar generation, that could be maybe abstract away, and you could also generate Python or whatever. But yeah, in case you're interested, I wanted to show you that syntax because that's useful.